Hello, welcome to the NPTEL online certification course on deep learning. For last few lectures, we are discussing about the different popular convolutional neural network architectures. And while doing so, in our previous lecture, we have tried to see that what are the challenges of deep neural network, and we were also discussing that how those challenges are addressed or can be addressed in different networks. So, we have talked about the challenges in deep learning, and let us just try to recapitulate that what are those different challenges that we have seen. So, the first challenge that we have said is deep learning is data hungry, in the sense for training of the deep neural network you need a large volume of data, maybe thousands and thousands or even lakhs of data for the training purpose, and all those data have to be annotated data. However, practically it may not be possible to generate sufficient number of data which will be used for the training purpose. So, in that case, what you have to go for, we have to go for data augmentation techniques, so that even if you have the limited number of data, by processing those data, we can multiply the data volume. And the kind of processing can be that you can take different crops or different portions of the data which is taken from the data which is already available for the training purpose, or you can employ different types of distortions on the given training data, but keeping its class same. Maybe you can take the mirror imaging of it, or you can modify the intensity, you can modify the color, and so on. So, that is how you can address the problem of generating voluminous data for training of the deep neural network. The other kind of challenge or the problem which is faced in deep learning is overfitting of the model or lack of generalization of the model. As the number of parameters in the deep neural network are very high, so it is quite possible that while training, the neural network will try to memorize the data which has been fed for the training, and in the process it does not really understand or really encode the structure or the features which are present in the data. So, to avoid this overfitting problem, there are different techniques which have been employed, and we have discussed many of them in our previous lectures. One of them we have said is that when you try to train an autoencoder network, one of the layers in the autoencoder network is a bottleneck layer, and the purpose of using this bottleneck layer is that whenever your training data or the information passes through the network, it passes to a constant region. So, as a result, the network does not or cannot simply memorize the training data, but it has to understand the structure or the features present in the training data, and that features can be used later on for recognition purpose or understanding purpose. Similarly, other kind of approaches to tackle this overfitting is having noisy autoencoder, where the training data, you add noise to the training data, so that the autoencoder tries to understand what is the inherent structure or salient features which are present in the training data, and using that it tries to recognize the image or it tries to understand the image. So, there are different such approaches by which the overfitting or lack of generalization that can be avoided. One of them is by having the generalization loss, incorporating a generalization loss in the loss function, where the generalization loss can be L2 norm of the weight vectors which are there in your neural network. So, there are various approaches in which the overfitting can be addressed, and we have discussed about those addresses in our previous lectures. The other problem that we have said is the vanishing or exploding gradient problem, and we have also said that this problem becomes very severe as the depth of the neural network becomes very large. the reason for this is that when you train a neural network or when you tune or update the parameters of the neural network, it is the gradient of the output error which is considered for updation of the parameters or the weights in the neural network. And why you take the gradient is, using the gradient descent approach, you try to minimize the output error with respect to the different parameters, and while doing so, you update the parameters in such a way that the output error is reduced. So, if I look at this next slide, which of course we have discussed in our previous lecture, that I have taken a very simple multi-layer neural network where every layer consists of one node and input is also a scalar. So, input is a scalar x, and because every layer contains only one node, so the activation that you get from every layer is also a scalar. So, going by this, your final output O over here, this output O will be basically the function f4 of W4 multiplied by f3 of W3 multiplied out by output of f2, where f2 is W2 multiplied by the output of f1, where f1 is the function of W1 times x. And each of these functions, f1, f2, f3, f4, they are basically nonlinear activation functions. So, if I want to update this input vector, this weight vector W1, so that the error at the output is reduced or minimized, then I have to make use of the gradient descent approach, or I have to find out the gradient of the output error with respect to W1. Similarly, for updation of W2, I have to find out the gradient of the output layer with respect to W2, and so on. And when you try to take the gradient of the output layer, a term comes which is gradient of output with respect to the corresponding parameter. So, suppose in this case we are trying to update the value of the input weight of the parameter W1. So, I have to compute what is del O del W1. And if you compute in this, following this chain relation in this function, you find that del W1 will be x1 into f1 dash into W2 into f2 dash into W3 into f3 dash into W4 into f4 dash. And the number of such terms in this product will go on increasing with the depth of the network. If it is 5, if the depth of the network is 5, then 2 more terms will appear in this expression, that is W5 and F5 prime, and so on. So, if you study this product, which is nothing but the gradient or the partial derivative of the output with respect to your input parameter, with respect to the parameter W1, you find that there are various terms which affects this gradient. And one of the terms are f2, f3, f4 and the derivatives of that. That means the nature of the nonlinear activation function used in these neural networks, they have a say on the value of this derivative. And the other factors are the weights W2, W3, W4 and so on. These weights also decide what will be the value of del O del W1. So, naturally, the nature of these nonlinear activation functions that decides what will be the value of this product. That is the reason that in case of deep neural network, instead of using sigmoidal function as a nonlinear activation, the nonlinear activation function which is mostly used in deep neural network is rectified linear unit. Because if I take sigmoidal function, then the maximum derivative of the sigmoidal function, as we have told in our previous class, is given by 1 by 4, which is already less than 1. And in this product term, you find that if all the terms are less than 1, then the final product will be very, very less than 1, which will be almost 0, negligible. And if it becomes almost 0, then when you try to update W1 as W1 minus delta times del W1, that del W1 terms will almost vanish, and as a result, the W1 will not be updated at all. So, the nature of this nonlinear function, f, that is very, very important, and why you use ReLU is the derivative of ReLU is equal to 1, when as long as its argument are greater than 0, right. So, that is why ReLU is preferred as the nonlinear activation in case of deep neural network. The other terms are the weights W1, W2, W3. So, naturally you find that if all of them are ReLU, nonlinear activation functions are ReLU, in that case this product becomes W2 times W3 times W4, because for ReLU the derivative of the nonlinear function is 1. And here if W2, W3, W4 all of them are less than 0, so let us assume they are 0.5. So, it will be 0.5 into 0.5 into 0.5. So, the product will be very, very less than 1. And that is what is vanishing gradient problem, because as you are moving towards the earlier layers, the value of the gradient goes on reducing exponentially. On the other hand, if the weights are greater than 1, then all of them multiplied together increases the gradient exponentially, and that is what is gradient explosion problem. So, in one case it is vanishing gradient problem, in other case it is exploding gradient problem, and both of them are bad for training of the deep neural network. And that is the reason it has been found that in many cases the deep neural network performance is worse than its shallow counterpart. So, to address this problem, either we have to choose the weights appropriately. So, there we have said that when you choose the weights at random initially, for if a node receives the input from say n number of nodes. So, if I have a situation something like this. So, I have a node over here in a certain layer, and it receives input from n number of nodes. Then these weights are to be decided at random, where the mean of the weights will be 0 and the standard deviation of the weights or the variance of the weights have to be 1 by n. So, this is the mean mu and this is the variance sigma square of the weight components that you want to assign at this layer. And in some cases, instead of 1, the variance 1 by n, the variance is also taken to be 2 by n. And that is rule of thumb how you decide or how you select the weights at random to the connection weights at any of the layers. And the other possibility, the other approach to tackle this vanishing gradient problem, as we said earlier, is by taking intelligent backpropagation learning algorithm. That means by having a proper architecture or the algorithm to be used for backpropagation learning. So, this is how what we are going to discuss today, that we will be discussing about two architectures. One is GoogleNet and the other one is ResNet or residual network, and we will try to see that how this vanishing gradient problem are addressed in GoogleNet as well as in ResNet. So, firstly let us talk about GoogleNet. In fact, in our one of our previous lectures, we have talked about VGGNet, that was particularly VGG16, and we have said that VGG16 was the first runners up in the visual recognition challenge 2014. And GoogleNet was actually the winner of ILSVRC, that is ImageNet Large Scale Visual Recognition Challenge 2014. So, let us see what this GoogleNet is. So, here this diagram shows the architecture of the GoogleNet, where every blue box represents a convolution layer, every red box represents max pool layer, the green boxes represent the feature concatenation, all the features that you compute from the convolution layers or after the max pool layers, they are concatenated together to give you a feature map. And at the output of the classifier, at the final, after the fully connected layer, FC layer, you have the softmax layer, which is used for classification. And as before, the number of nodes in the softmax layer is 1000, one per image category in the ImageNet database. And if you look at this GoogleNet architecture, you find that there are 22 layers with parameters. So these layers are actually convolution layers and fully connected layers. And if you also consider the max pool layers, obviously the max pool layers does not have any tunable parameters, then the total number of layers that you have in the GoogleNet is 27. And you can compare the architecture of GoogleNet with the VGGNet, right? So this is what is GoogleNet architecture. And if you look inside GoogleNet architecture, you find that there are a number of units which are almost repetitive. So for example, this is one unit, this is another unit, this is another unit, and so on. So there are 9, 1, 2, 3, 4, 5, 6, there are 9 such units in the Google network, and these units are almost identical. So these units are actually inception units. They are called as inception units. So let us proceed further. So what are these inception units or inception modules? You find that these inception units or inception modules, they actually compute the features which are used in the Google network. And if you look at the way they work, or the number of different types of convolution units they have convolution kernels of size 3 by 3, convolution kernels of size 5 by 5, and also convolution kernels of size 1 by 1. So GoogleNet actually introduces a 1 by 1 convolution kernel, and we'll see that what is the use or what is the advantage that you gain using this 1 by 1 convolution kernel. So this is what is the inception unit. You have the different convolution layers, you have the max pool layers, and finally outputs of all these different convolution channels or feature convolutions are actually the operations to extract the features, right? That is what we have seen earlier. So finally, in this inception module, the different features which are computed by different convolution kernels, they are stacked together to give you a feature map. So here what we have is depth concatenation. All the feature maps given by different convolution channels or different feature channels, they are stacked one after another to have the final feature map. So let us proceed further to see that what are the things that we have in this inception module. So this inception module has 1 by 1 convolution kernel, it has 3 by 3 convolution kernel, and it has 5 by 5 convolution kernel, and all these convolution kernels are within the same inception module of the network. And this is a concept which is called network inside network. So I have inception networks or inception modules which are networks by themselves, which are within the entire GoogleNet. Now, when I have larger convolution kernels cover a larger area to compute the features. So when it is 5 by 5 convolution kernel, it covers a receptive field of 5 by 5 pixels to give you the features within those 5 by 5 pixels. Similarly, if you use 1 by 1 convolution kernel, then 1 by 1 convolution kernel actually gives you the further details which are present in the image. Okay. So this 1 by 1 convolution kernels gives you the most accurate features, whereas if you use the convolution kernel size, you get a feature which is over a trend or over a larger area of the image. So as you vary the convolution kernel size, say 1 by 1, 3 by 3 to 5 by 5, you are actually extracting the features at different scales, starting from the finest features in 3 by 3 to the coarse features given finest features given by 1 by 1 convolution kernel, to the coarse features given by 3 by 3 and 5 by 5 convolution kernel. When you use 1 by 1 convolution kernel, that also reduces the amount of computation that you have to perform. Let us see how this 1 by 1 convolution kernel reduces the amount of computation that you have to perform. So, let us try to see this. Suppose I have an input feature map which is of size 14 by 14 by 480. So, there are 480 different feature maps of the channels which are concatenated together, and size of every feature map is of size 14 by 14. And from there I want to extract features which are again 14 by 14 by 48. That means size of every feature map remains the same, which is 14 by 14, but the number of channels are reduced to 48. So, this can be done in two ways. Either use it directly by using 5 by 5 kernels and 48 number of such kernels, of course with STIDE. So, each of these 5 by 5 kernels gives you, with STIDE and appropriate padding, gives you a feature map of size 14 by 14 by 1. Each of these 48 channels, each of these 48 kernels will give you a feature map of size 14 by 14 by 1, as I said, with appropriate STIDE and the corresponding padding operations. And each of them gives you one feature map. So, when I have 48 number of such kernels, I get 48 feature maps. You stack them together, you get 14 by 14 by 48 number of kernels. The other way is that, suppose this is just one of the ways this can be done. There are numerous possibilities in which the same can be implemented. So, one of the approaches, first let us assume that we will have 1 by 1 kernel, and each of this 1 by 1 kernel will give you 14 by 14 feature maps, 14 by 14 by 1 feature maps, and if I use 16 such kernel, I will get a feature map of 14 by 14 by 16 by stacking the outputs feature maps computed by each of the kernels. And then from here, at the second level, I can have 5 by 5 kernels. So, each of the 5 by 5 kernels will map this feature map 14 by 14 by 16 to 14 by 14 by 1, of course with proper STIDE and proper padding that we have already discussed before. So, each of this 5 by 5 kernel is giving me a feature map of size 14 by 14 by 1. If I use 48 number of such kernels, then I will have 48 such feature maps, each of size 14 by 14 by 1. You stack 48 such feature maps together, you get a feature map of 14 by 14 by 48. So, you find that here also I get 14 by 14 by 48, here also I get 14 by 14 by 48. Now, if you compute the number of operations that you have to perform in both of these options, you find that when I use this option, that is directly from 14 by 14 by 48 to 14 by 14 by 14 by 14 by 480 to 14 by 14 by 48, using 48 kernels, each of size 5 by 5, the total number of operations that I have to perform is 14 into 14 into 48 into 5 into 5 into 480, that gives you around 112.9 million operations. Whereas, if I first use this 1 by 1 kernels followed by 5 by 5 kernels, for the number of operations that you perform with 1 by 1 kernels is around 1.5 million. You can compute this to verify, and subsequently with 5 by 5 kernels, the number of operations is around 3.8 million. So, the total number of operations in this option becomes this plus this, which gives you total 5.3 million operations. So, you compare this with this. For direct conversion or direct mapping, I need 112.9 million operations, whereas using initially this 1 by 1 convolution layers, convolution kernels, the total number of operations comes down to 5.3, and which is obviously much less compared to 1 order less. It is just 5.3 against 112.9. So your computation has been reduced drastically. So this is one of the advantages that you get using one by one convolution layers. Uh, so once you do that, then finally what you have is the output of these filters, each of these channels are then stacked together to give you the final feature map. So every inception module is acting as a multi-level feature extractor, and you see there are 9 such inception modules, and this GoogleNet gave a top 5 error rate of less than 7%, which is of course marginally better than what you have got in case of VGGNet. So this is what the Google network. Now let us just see that how this GoogleNet tries to tackle the vanishing gradient problem. So as we said that the final layers in the GoogleNet, which is over here, they are actually classification layers. And you look at that this GoogleNet gives you 2 more classifiers which are known as auxiliary classifiers, which are added in the middle layers, and these are the auxiliary classifiers. So these auxiliary classifiers have this fully connected layers. It has the softmax activation layer, then output of the softmax activation layer is actually your classifying output. So what is the purpose of having these auxiliary classifiers? You find that as we have told before, that you have the vanishing gradient problem because of the depth of the network. While training, as we try to propagate the error or the gradient towards the early layer of the network, the gradient almost vanishes. And these auxiliary classifiers are basically smaller convolution networks, CNNs, which are put on top of middle inception modules. So this addition of auxiliary classifiers in the middle layers, on top of the middle inception modules, actually tries to exploit the discriminative power of the features produced by the layers in the middle. So as they are classifiers, they will also give a classification error, and these classification errors are computed from the middle level inception modules. So while backpropagation, when you are performing the backpropagation learning, the loss computed from these auxiliary classifiers are added to the total loss of the network. And of course, these auxiliary layer outputs, the loss from the auxiliary layer outputs, are scaled by a factor of 3 and then added to the final loss functions. And because of this, because you are computing the loss from the middle layers and adding to the final loss function, and that is being used during the backpropagation operation. So this is expected that the vanishing gradient problem will be solved to some extent. Of course, these auxiliary classifiers are used only during the training of the network. Auxiliary classifiers are not used at the test time or at the inference time. So we have seen that in case of GoogleNet, what is the architecture of the GoogleNet, and using auxiliary classifiers, how the GoogleNet tries to tackle the problem of vanishing gradient. So in our next class, we will talk about the ResNet or residual network, and we'll see that how this residual network also tries to address the vanishing gradient problem. So we'll stop here today. Thank you.